Okay, so today we're going to be going over exam 2 review part 1. This whole page is going to be your reactions page, and I give you a lot of the reactions that we're going to be seeing in our second exam, so it's good variety. Okay, we can start with the first one. The first one is cuprates, and actually I'm going to start with the second one because I feel like it'll provide like the basics on the cuprates. So I'm going to show you the mechanism for this one. Okay, perfect. Okay, so right here in your reagents, you have a cuprate. So cuprate is positively charged, meaning whatever is going to be next to it, like on the left side, is going to be negative because you can't have two like charges together, right? So then it's going to act as a partial negative. So your carbon is going to be the nucleophile in this case. So then what I'm going to do is from this carbon nucleophile, I'm going to attack the carbonyl carbon and break open the carbonyl group. So I add a new methyl group, so I'm going to do CH3. I add my new methyl group. And I still have a negatively charged oxygen. And so usually from here, we would protonate using this H2O, but we have a good leaving group on here. Cl is a good leaving group, a really good one. So what we're going to do is we're going to reform the carbonyl and kick off the leaving group. So we didn't even have to use the H2. Right, so I get a ketone. And so usually we would start attacking again, but that's with the stronger organometallics because this organometallic is a pretty weak one. Weaker. So it only attacks once. All right. Then I'm going to go to the top. So I think one of the exceptions to the organometallics is for the cuprate. And so when you have an alpha beta unsaturated compound like you do on the left, you're going to add, it's going to be like 1,4 addition. You're going to add to the fourth part. So let me teach you what an alpha beta unsaturated is. Let me see. Let me give you, this is an example. So it's a ketone, right? And so any carbon, like one carbon away from your ketone is going to be an alpha carbon. So this is one carbon away from my ketone, it's an alpha. As well as the one on the left, it's also one carbon away from my ketone, so it's alpha. One other carbon away is going to be beta. And you can keep going with the Greek alphabet as you keep going farther away from the carbonyl group. But this is just showing you like a bit of the nomenclature to it, I guess. So then if I'm looking back at my example, I'm looking at my carbonyl. One carbon away from my carbonyl is the alpha carbon. So this is an alpha carbon, and this is an alpha carbon. 2 carbons away from my carbonyl is going to be a beta carbon. So this is my beta carbon. So then between your alpha and beta carbons, you have a double bond. And the double bond is, or like unsaturated is a code word for double bond. So that shows you that this is an alpha beta unsaturated compound. And so 2 alpha beta unsaturated compounds, when we react it with a cuprate, all that's going to happen is, let's see, your carbonyl stays the same, any other substituent stays the same. The double bond is going to be removed, and you're going to add all of this part to your compound in the fourth position. So you would count it as like 1, 2, 3, 4, and it'd be like 1,4 addition, kind of. So you would add it to the fourth position. My recommendations for this is to count your carbons. So usually, like, I think when I first, or some of the things that I've heard from other people is that they think there's like 1, 2, 3 carbons that we should add to this compound. But it's only really the things within the parentheses. So only these 2 should be added. So there's 2 carbons that are going to be added, and those carbons have a double bond. So that's exactly what I'm adding right here. 1, 2 carbons. And it looks a little weird because we added this bond, but that's the necessary bond to make sure that you have the 2 carbons. All right. Let's go to this next one. So here we have Tollens reagent. And so what Tollens reagent does is it goes from, it's selective for aldehydes, and it turns them into carboxylic acids. So then all that's going to happen right here is it's going to go from benzaldehyde to benzoic acid. Selective for aldehydes, makes carboxylic acids. There you go. That's how that happens. This next one is, I feel like, I'm not sure if I got this on my test. I'll check, but this is one of the weird ones that I saw when I was in Oakland too. So usually like with the LiAl, lithium aluminum hydride, you would attack the carbonyl and make an alcohol, right? So here, when you have an amide, like how you do here, this is the amide functional group. All that's going to happen is you keep the amine group, so NH2 remains, all the carbons remain. The only thing that happens is the carbonyl goes away, so minus C double bond O. All right. So this next one, something that helped me when I was looking at like a lot of these questions, because look at these next three questions. Yeah, it's just these three. They're with like my amines and enamines. So what helped me was knowing like the chart, like what creates what. So let me go over here. So if you have a primary amine, you make an imine. An imine is a group that looks like this. So I'm going to draw a random imine. This is a random imine. And so here, there's a double bond directly on your nitrogen. So this is an imine. When you have a secondary amine, you make an enamine. And this is an example of an enamine. Let's see, make it better. Okay. That's an example of an enamine. So you have a carbon-carbon double bond and just a nitrogen single bond. So one carbon away from your nitrogen, you have a double bond. And so let me see. Something that you should notice right here is that there's only one thing on my imine on the top part. So this is why, like, this is the primary amine that's going to be added to our carbonyl compound. So then what you would use for like this reaction to make this compound right here, I would use this carbonyl and NH2 with a methyl group. So this is a primary amine and a simple methyl group that all you're going to do is attach to that. Did I say that? Simple carbonyl group that you're going to attach to that. And so to make this one right here, I'm going to use a secondary amine, and you should notice that the two R groups that are away from your carbon are going to be like away from the carbon double bond are going to be the groups that are going to be on your amine. So two methyl groups and a hydrogen, because you can't forget that hydrogen, or else it'll be like it'll be positively charged. Negatively charged. There you go. Okay. So it'll be a secondary amine and a simple carbonyl group that, or a simple ketone, that will make that enamine. So I think this chart really helped me. And every time I would see a problem having to do with enamines, imines, amines, or anything, I would write like, okay, what is this compound? So this compound on my left is an imine. And I know that with imines, they're made up from primary amines. Okay, cool. So then what this question is asking you is what compounds are basically used to make this imine? Because H3O plus breaks up this imine into like the components that would have made it. So then all I would do is recognize that this double bond right here is going to be attached to my oxygen. And I'm going to break it off. So my two carbons, nitrogen, and it's a primary amine, so I'm going to add my two hydrogens. So it's a primary amine, we're good there. And then the carbonyl group that's going to be there is looking like this. There you go. I'm just going to add a hydrogen here, just because I think it looks prettier. So then those are the two components that would make up your imine. Okay. Now let's try this next one. Same thing here. We have an enamine this time because the double bond is 1 carbon away from my nitrogen. I'm going to block out the R groups and the amine that are not connected to this group right here. This one's a little bit more a little bit harder to recognize how the carbonyl, what carbonyl we're going to be using and what secondary amine we're going to be using. So yeah, let me write that already, secondary amine. But this is what usually I like to do. So I see that the carbon-carbon double bond, and this carbon-carbon double bond is one carbon away from my nitrogen. So that's basically where I'm going to stop. That's where I'm going to add my ketone at this group right here, at this bond right here, is where I'm going to add everything else. Or I'm sorry, stop the find the line between our two reactants. This is what I did there. Okay, so then that'll be there. And I know I have a secondary amine that usually makes it, and all I'm going to do is write my ethyl group and my methyl group with a hydrogen, because or not, it's going to have, if you don't write the hydrogen, it's going to have a negative charge. Okay, so let me see. Yeah, those are a bit more difficult. I would, I think this one is a bit more difficult to understand and see what's happening, because you can't break it in half like how we did on this one. So I think a little bit more practice on those, but hopefully that helped. Okay. This next one, we have a ketone, we have a primary amine, and we know that primary amines make imines, right? Okay, so let's see what I can do. Yeah. So then all I'm going to do is I'm going to redraw my ketone structure, the R groups on it. And I'm going to cut off this oxygen, place my double bond where it usually is, and I'm going to attach my nitrogen compound without any hydrogen. So just this. It's a total of 3 carbons. Let's not drop any carbons. What's 1, 2, 3? Yeah, that should be good. And let me highlight, or let me trace what gave me what in the products. So I cut off the oxygen from my ketone group, and I inserted the amine without the hydrogens where the oxygen should have been. And that's all I did. That's the trick for the reactions page if you had one. Okay. This next one was something that I had the mechanism problem on, so I had to write it out and everything. And I'll have the mechanism problem in the next YouTube video that I do. But for now, I'm just gonna do the reactants. And if you kind of don't understand this now, I would recommend that you go to the second video before you do this question. Okay. But it's not too bad when you're doing it in the reactions page. So all you have to do is you're going to cut off the phosphorus with the 3 phenyl groups on the side. So cut that off. And you're going to cut off this oxygen right here. And what you're going to do is these double bonds are going to merge. This is just the trick for the reactions page. This is not what's actually happening in the mechanism and everything. I'll show you what happens in the mechanism. So I'm going to do this right here. Actually, double bond. And then the other side of my double bond is like this. So I'm going to trace this. Right, so I kept all my carbons, and all I did was cut off the double bonds in both of my groups and pasted them together basically. So that's the trick for the reactions page. This next one is, I think it's a really good one. So NaBH4, sodium borohydride, is it's a reducing agent, and it's selective for ketones and aldehydes. So selective for ketones. Ooh, that's bad. Okay. And aldehydes. So if it's selective for ketones and aldehydes, what I'm going to do is I'm going to like analyze my compound that I'm reacting it with. And I see that I have an ester group here and a ketone. So then all that's going to be reduced, because this is a reducing agent, is going to be my ketone. So then when I draw my product, my ester group should remain. Ester group remains. And my ketone is going to gain a carbon-hydrogen bond and an alcohol. There you go. So it reduced the carbonyl from the ketone. Only that one. Because it's selective for aldehydes and ketones. Okay. For this next one, I think this is the only stereochemistry for Doherty's exam, because this one is like stereoselective groups. So this one was a bit confusing when I was learning it, but it was just something I had to like memorize. So the SCBS, you would think like, oh, it's going to give you the S enantiomer, but it's actually going to be giving you the R enantiomer. And so same thing with the R, you would think you would be like, oh, it's going to give me the R enantiomer, but it's actually going to give you the S enantiomer. Okay. So then just redraw everything, and these are like reducing agents. And so when it reduces, it's going to form a new stereogenic center, and so that's basically what we're going to decide, like, oh, this is going to go as S, or this is going to go as R. So then when I'm drawing the R enantiomer, like, she has tricks to it, but like, to be honest, I like on a scratch sheet of paper or something, I'll just write like the base group to it, and I'll just guess. Let's see. And then I'll be like, okay, if this is the R enantiomer, I'll draw it here. If this is the S enantiomer, I'll draw it here. So just because I don't know. I always do that. So then I'm going to show you how to do priority, because I feel like this was something that someone's asked me before, and I was like, okay, quick reminder. So then this is my stereogenic center, and so numbering priorities by the highest amount of mass. So then I'm going to look at my atoms, one atom away from my stereogenic center. So that's oxygen, it's carbon, and that's hydrogen. So then out of the carbons, hydrogens, and oxygens, my oxygen has the highest amount of molar mass, so this is number one priority. Hydrogen has the lower amount of molar mass, so this is the lowest priority. Then it's harder to decide like what is going to be secondary, second or third priority. What we should notice is we're going one carbon away from the stereogenic center, and we have the two same things, so a carbon and a carbon. So then you go one more atom away, and you see what's there. So if I go one more atom away from this carbon right here, I have a hydrogen. If I go one more atom away from this carbon right here, I have a carbon double bond. So then I'm going to say that this one has the higher priority to this one. So then that was like a quick reminder of that. So I trace 1, 2, 3, and ignore 4. So I'm going anti-clockwise, and it is the S enantiomer. Because clockwise is all right. Okay, so then S enantiomer, so this does not go here. This actually goes where? Okay. So then I do the opposite thing on the other one. I draw my base compound. Okay. And then instead of my OH being on a wedge, I'm going to draw it on a dash. Draw my OH on the dash. I'm gonna draw them. OH on a dash. OH on a wedge. And that should be my R9 tumor. There you go. And I can just check really quick. So this is 1, 2, 3, 4. Priorities stay the same. Trace 1, 2, 3, 4. Anti-clockwise, but H is going towards me. So H is on the wedge. So then you go from R and you switch to S. I mean, go from S and you switch to R. So this is the R9 tumor. Cool. This next one is cool. Okay, so H2PDC, so hydrogenating. Hydrogenations are going to be different when you use them in different amounts. Like the product's going to be different. So for this one, I'm going to ask you to do an excess. And for this one, I'm going to ask you to do one equivalent. And then cross out this top one and put Li, lithium aluminum hydride. So 1 and then 2, H2O. So then the first thing I'm going to do the one equivalent first. So for the one equivalent, the only thing that's going to change is the carbon-carbon double bond. So that carbon-carbon double bond is going to be hydrogenated. And so that means that you're basically adding hydrogens to each side of the double bond so that it's no longer unsaturated and it'll be saturated. But that's the only thing that's going to change. The carbon-oxygen bond is a lot stronger. So if you only have one equivalent, it's going to choose to the hydrogenation is going to happen to the weaker bond, which is carbon-carbon bond in comparison to the carbon-oxygen. So then that's how it does with one equivalent. But if you have it in excess, everything is going to be reduced. So then same thing happens. Carbon-carbon double bond is going to be hydrogenated. So one carbon in each side, and we have no longer a double bond. And then for the ketone, it's also going to be reduced. And so when you reduce a ketone, it's basically like if you're doing the lithium aluminum hydride to a ketone. So you're adding a hydrogen, but you can't get rid of that oxygen. So all you can do is reduce it one time to have an alcohol group. So double bond leaves, and we have an alcohol in place of the carbonyl group. And then I'm going to do lithium aluminum hydride. So we know that lithium aluminum hydride doesn't do anything to double bond. So the double bond is going to stay in this case, but it does react with the carbonyl carbons. So then in this case, I'm going to reduce only the carbonyl carbon to an OH group. And yeah, that'll be it. You can only attack once to that carbonyl, so that's all that's going to happen. So then notice how you have like different products on each of these. And I think the like main takeaway from this one was looking at the H2PDC and how the like concentration of those reagents will matter in the products for your reactions. Yeah. Okay. These are a bit of the harder ones that you can definitely see in your exam. So Mg ether. I'll do this one first. This one right here. Mg ether, all it does is it creates the organometallics. So ether is like the solvent in this case, so it helps the Mg go in between the Br. So for the first step, all you're doing is creating your organometallic. For the second step, you're going to react this organometallic with an epoxide. And so remember, in epoxides, we would usually attack the least sterically hindered side, but they're both not sterically hindered, so we can attack whatever side we want. And so the attack goes from the bond of the carbon with the Mg, because Mg is a metal, it's positively charged, and so anything near it on the left side or on the right side has to be negatively charged, or else those charges will repulse if they're the same charge, right? So then our carbon is going to act as the nucleophile, and we're going to attack from the carbon Mg bond to the carbon on the epoxide, any of the ones that we want, because they're not sterically hindered. And so when I attack, we already had 2 hydrogens on both of these carbons. And if I form another bond to that carbon, I'm going to break the octet rule. So then what I'm going to do is I'm going to attack, and I'm going to put the electrons on this bond on oxygen. So then what our product should look like is, let me number it. So I'll do 1, 2, 3, 4, 5. Whatever numbering system helps you will help you on the test, but this is what would help me. So then I'm doing 1, 2, 3, 4, 5. And on 5, I have an oxygen with a negative charge. So then let me number 1, 2, 3, 4, 5. Yeah. And then yes. On the carbon number 5, we have the negatively charged oxygen. So for step 3, all we're doing is protonating. And so step 3 is going to result in our product. And our product should look like this. There you go. Can we count just in case? 1, 2, 3, 4, 5. Yeah, we're good. So then I'm going to do this next one. So first step again, the Mg ether is going to help you make the organometallic, so the further Grignard's reaction. So the first step is going to make the Mg go in between the Br and carbon. This is for first step. Second step, you're going to react it with CO2, which looks like this. So everything the same happen, like everything is going to happen the same way. So carbon is nucleophile in this case, so it's going to attack the carbonyl carbon. This is a carbonyl carbon. It has 2 carbonyls on it. You can't have 5 bonds to a carbon, so I'm going to pop one of those bonds, and leave the electrons on an oxygen. So then what my compound should look like at this point, let me number 2, 3, 4. 1, 2, 3, 4. Double bond on my 4th carbon and negatively charged oxygen on my 4th carbon. 1, 2, 3, 4. There we go. And so last step, step number 3. Step number 3 is just protonation. So then I'm going to write everything the same and protonate my negatively charged oxygen. Count my carbons, 1, 2, 3, 4, and we're good. That should be our answer. Then I'm going to go to this top one. This top one is a little bit different. This is one of the trick questions that would definitely put on your exam. So then, first step, just making the organometallic. So then, boom, boom, MgBr. Second step is reacting it with an acid. Okay, so let me remind you of something like this. So we have a carboxylic acid, so it's an acid. And we have a base, a very common base we see is like this right here. But it can also be something that, I mean, like in Gen Chems, we usually wouldn't see this. We would usually see like the hydroxyl groups attack, and we would never see like an amine. So this is like a different view on bases. But we know that this would usually like react and do an acid-base reaction. So it would look like this in the products, negative charged, and NH4 plus your new conjugate acid, your new conjugate base. So that's like a summary of acids. But like what I'm trying to tell you from this is like the base doesn't always look the same. So it can always be different, and it's always like it's usually something that has a negative charge. So then on my organometallic, our organometallic can't or usually acts as a nucleophile, but here it can act as a base. So then I have my acid group right here, and I'm going to react it with my acid. And instead of this carbon nucleophile, it's going to act as base and deprotonate this oxygen right here. So then my product should look like just like that. You have a total of 1, 2 bonds right here, 2 hydrogen, and you're adding 1 more to make an alkene. So it has 1, 2, 3. So that's your alkene. Your MgBr goes away. And what I think you can do is I think you can So you deprotonate your acetic acid. You deprotonate your acetic acid and it becomes acetate. So I'm gonna draw my products over here, and this is my acetate. So I suggest you draw your both of your products, like if they asked you this on the reactions page. So I drew my carbon hydrogen bonds. I drew my conjugate base, and I'm going to put this MgBr plus, because Mg usually has a 2+ charge, right? And bromine usually has a minus charge. So if you combine those together, it's going to be MgBr with a leftover plus charge. So then what I'm going to do is I'm going to use this plus charge to make my negatively charged acetate neutral. So that I'm going to draw all of this together, and this is going to be my product. I would suggest you draw both of your products. Okay. These last ones are going to be about acetal groups. So acetal groups, I think something that you should like always remember is what they look like. So this is let me get the word for it because I always mess up. Acetal. Let's see. I don't even saying something completely wrong. I'll give you some of my notes too, because I made cheat sheets for like cheat sheets, meaning like to help me memorize, not to actually cheat. But I would make those, and they'd help me like big time with my exams. So I recommend you guys do those, especially for this exam because it's a lot of memorization. Acetal or I'm gonna say acetal. I'm gonna say acetal. Or whatever pops up when I say it. So this is an acetal. So it has 2 ether groups on it, 2 ether. And this is a hemiacetal with an ether and an alcohol group. And so what we're looking at is this carbon right here to tell us like, oh, this is an acetal. So to this carbon, we have 2 ether groups, so it's an acetal. Or to this carbon, we have an alcohol and an ether group, so this is a hemiacetal. Hemi means half, so half of it is in the acetal formation. Okay, so then I like to identify what we have first on our left hand side, so for our reagents. And for the left hand side, I already have a hemiacetal. And it looks weird because we're like not used to this, I don't know how to say it, cyclization, okay? But notice how this carbon right here is attached to an alcohol group, alcohol, sure, and an ether. So it's a hemiacetal. So then if I add one more alcohol group with an acid to it, what I'm going to do is I'm going to make it a full-on acetal. So I'm going from a hemiacetal to an acetal. Let me see if I can get this mechanism down for you guys. So this is my acid. This is going to act as a base, deprotonate to make water. Maybe closer. Oh, there's an oxygen that goes there. And so I make a good leaving group. And so this good leaving group is going to make my carbon more like a more, what is it called? I don't know the word for it, but it's going to make the alcohol group, the neutral alcohol group, attack a lot easier than it would have initially. Because usually we would not like see something like this happen. But since it made it easier for the attack, that protonation made it easier for the attack, what's going to happen is actually going to make an attack. you're going to have the alcohol connected to it. So all of this, but it has a plus charge. And so how we're going to get rid of this plus charge is we are going to use this is like thought of as like a catalyst in this point. So catalysts have to regenerate. So when we deprotonated this right here, it formed H2O by itself. So this H2O is going to come back and deprotonate to make this a neutral compound. So all these arrows are probably confusing me, so sorry about that. Just follow along with my words, even if I'm. Okay. And that should be your product. So now we look at this carbon, we have two ether groups attached to it, and we made a full-on acetal. So keep in mind what you're going from to, what you're going from. So hemiacetal to acetal with only one equivalent of an alcohol. And so I'm gonna look at this one here, and we have two equivalents in alcohol. Two equivalents. And the reason we have two equivalents, we don't see like 2 moles of this compound, but we do see 1 alcohol, 2 alcohol, so 2 equivalents of an alcohol. So then if I'm just looking at my carbonyl, I'm checking with 2 equivalents in alcohol, we know I'm going to make an acetal. Whereas if we only attacked with 1 equivalent of 1 alcohol, like without all of this, we would make a hemiacetal because there would only be 1 alcohol attacking. Okay, so then I'll show you the mechanism for this one too, because I feel like that would help. This might be a long mechanism. Okay, so TSOH acts as an acid, so I'm gonna just draw like a proton. So this oxygen is going to steal this proton. And so I now have a positively charged oxygen, making it easier for a neutral nucleophile to come and attack. So that's exactly what's going to happen. This neutral nucleophile is going to come in and attack my carbonyl carbon. And so I get this. O with 2 carbons, OH, H group. So good. We're good right now. Okay. So then what I'm going to do is I'm going to do an intramolecular acid-base reaction, or we call this proton transfer. So right here I have a base, and right here I have an acid, positively charged acid. So this base is going to come and attack this proton, leave electrons on my oxygen, and form a good leaving group. So we have a positively charged oxygen, good leaving group. This is one that we usually see often. So we have a good leaving group, meaning that something can, again, come in and attack, something neutral can come in and attack this carbon right here and make the leaving group leave. So then I go up, and I now have boom, 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 oxygen, boom. And so I'm gonna count my carbons just to show you like what's happening. These 2 carbons are forming, like it looks weird, but you just count your carbons, then that will pretty much help you see like how you made this thing. And we usually call this acetal, man. So it looks like a little upside down man. Yeah, this would be your answer for this one. So we're doing the same thing with this top one, same mechanism and everything. We have 2 equivalents of an alcohol, so we know that we're going to form an acetal, not a hemiacetal, an acetal. So then I go from my carbonyl group and pop it open to form a full-on acetal. And I count my carbons, 1, 2. I have a total of 1, 2, and 1, 2. So they attack the carbonyl 2 times, and you form this full-on acetal. This is an intramolecular acetal reaction. So here it looks a lot different. So I'm going to do the mechanism for this one as well. Hey, two. Okay. So H0 plus acid So my nucleophile is going to come and get my acid. I'm going to draw this. Say, I'm going to count 1, 2, 3, 4, 5, 6, because I already know how it's going to attack. And I'll show you at the point where you would probably number it, because if you haven't practiced a reaction like this, you probably wouldn't think this is the first thing you should do. Like you should number oxygen number 1. So, but this is just going to help me not mess up. 1, 2, oops. 1, 2, 3, 4, 5, 6. Positively charged oxygen makes it easier for a neutral nucleophile to come in and attack. So your neutral nucleophile, in this case, we don't have anything else under or over our arrow. So in this case, whatever is inside my compound is going to be an intramolecular cyclization. So intramolecular means like within the compound, and the cyclization means you're going to make a cyclic molecule. So then I do see that I have an alcohol here, and how we've usually been doing is we've been counting alcohols to see how we're going to react. I have only one alcohol, so I know that I'm probably going to make a hemiacetal once this reacts. So then that's what I'm going to do. This alcohol is going to come in and attack my electrophilic carbon. You're forming something like this. I'm going to count my carbons. I went from, oops. This is number 1, 2, 3, 4, 5, 6. Notice how at number 1 right here, we're forming an attachment to carbon number 6. So that's exactly what we did here, 1 to 6. We still have a positive charge on our oxygen because we can't leave this thing right out. And when we attack this carbon, this is going to pop out because you can't have 5 bonds to a carbon. So then I have an alcohol group right here. Okay. Last step to this is you have a positively charged oxygen. We don't really want that. And again, our acid usually acts like as our catalyst here. So then at the first step, we deprotonated this acid right here, and we got a conjugate base of H2O. So what H2O is going to do is it's going to come back and take away this hydrogen so that we can form a neutral compound and we can reform the catalyst, because that's what you usually do in reactions. You reform the catalyst. And then again, what you should notice is this compound only had 1 alcohol in it. We only reacted it with 1 alcohol. So then we made a hemiacetal, not a full-on acetal. If there would have been 2 equivalents of an alcohol, then we would have made an acetal. Yeah. These are a lot of the reactions that I think I saw in my test. Like I have my test with me, and I got a lot of them off of there. I got a lot of the ones that I thought would be like exceptions that they could add to your test if they wanted to make it a little harder. So these were like a summary of all of the reactions that you should know. And what I recommend you guys do is I recommend you guys do like a cheat sheet. So I made cheat sheets for myself all the time. Let's see an example of one. So this is an example of one. You're not going to really be able to see it, but this is, I think, for chapter 18. And so I would just get a blank sheet of paper, printer paper, and I would put a whole bunch of reactions with whole different reagents and see how they reacted. And I did I did a lot of the exceptions. I did a lot of the things that I was confused on, and it really helped me. So I think it'll really help you if you do this. And I'll send this in the group chat as well, so you guys can get a quick look at it. But this is like what I really recommend you do for this exam. Okay. Cool. And then I'll make the part 2 in a little bit. So I'll see you guys later.